Hello, good people. Welcome to video number one of Unit 6, Section 13. So here's getting to the end of Unit 6. We're talking about improper integrals. Before we get into improper integrals, I guess let's talk about proper integrals, right? We know that whenever we're looking for an integral from a starting point to an ending point of some function, dx, what that really means is that we're looking for the area under the curve, whatever the function looks like. And I'm just going to do a random f of x here. Whatever the function looks like, if I start at 3 and I end at 10, then this would be the area that's under the curve, right? That's what a definite integral finds. Well, improper integrals mean that, and I think this is the big idea you need to walk away with. Whenever we're talking about improper integrals, there's always infinite behavior. Now, the infinite behavior can be due to my limits of integration being infinity. So, for example, if I take the integral from, let's say, 1 to infinity of 1 over x dx, this is an improper integral because when I draw it, if I draw 1 over x, that would be this function. Let me use a different color so that we can separate the graph from the function that we're talking about over here. So we're talking about this at 1 over x, but we're saying we're starting at 1 and we're shading all the way forever to the right. And so I have an infinite space here that I'm shading. But the question is, does all that shading add up to something? And that's what we're going to find with improper integrals. Sometimes they do, sometimes they don't. So in this example, the infinite behavior is due to one of my limits of integration is telling me to go on forever and keep just shading to the right. Or I could have an integral that goes from -1 to 1, let's say, and when I'm going to use the same function 1 over x dx, since we know what that graph looks like, this rational function looks like, well, let me make it a little bit closer to the axes there and a little bit closer to the axis there. So this is what it looks like. But wait, if I'm looking for the area between -1 and 1, that means I'm starting at -1 and I'm going to +1. But that would mean that I'm shading like an infinite number of space here and an infinite number of space here. Is that infinite number of space equal a number? Do they cancel out? But again, the infinite behavior, not because my limits of integration are infinity, but because there's infinite behavior in the graph due to a vertical asymptote. So how do we get around that? Improper integrals can be evaluated, and if they can, they're called convergent. And the way we're going to do that is by reintroducing something from the past. And that would be the limit. We're going to say that an integral whose top or bottom limit of integration is infinity, we're going to replace that by getting closer and closer to infinity using a limit. And so we're going to say this is from a to t of f of x dx. Or if my limit of integration is on the bottom, then I would say the limit as t approaches negative infinity from t to some value b of f of x dx. So either way, wherever the limit is, wherever the infinite behavior is, whether it's a bottom limit or a top limit, I'm going to use a limit in order to evaluate that. This is getting a little tricky. Well, whenever we deal with infinity, we do get some trickiness. So here's our function, 1 over x to the fourth. So we'll start with this example. So y equals 1 over x to the fourth. This is what it looks like. I want to find the integral from 1 to infinity. So starting here at 1, and then shading everything as it gets closer and closer to the x-axis. Forever, right? I keep shading all the way to the right and beyond. Does that area exist? Is it a finite number? Or am I just going to keep adding more area and it's just going to be an infinite area forever and ever and ever? And so here is how we do that. Let us change this limit or let's change this improper integral using a limit. So I'm going to say the limit as t approaches infinity from 1 to t of 1 over x to the fourth dx. Okay, so now I'm still taking the limit, so I can't forget this. But now I'm going to take the antiderivative of 1 over x to the fourth. Well, it might be easier if I rewrite this as x to the negative 4, so that I can take the anti-power rule, right? The reverse power rule will give me the antiderivative. So I add 1 to the exponent, divide by the new exponent, but I still need to evaluate from 1 to t. So I still need to plug in the top number, plug in the bottom number. And I need to take the limit of all of this business. Okay, so let's keep going. So I'm still taking the limit as t approaches infinity. This, if you don't mind, I'm going to rewrite it back to the way it was, which is x to the negative 3 was really x to the positive 3 on the bottom, and then I would be left with 1. So then let me rewrite this right now. This would be 1 over negative 3x to the positive 3. And now I'm going to substitute the top limit. So it would look like this, minus substitute the bottom limit. 1 over negative 3, 1 to the third. And I'm still taking the limit of this thing. Well, if I take the limit as t approaches infinity of this first part, what's going to happen to the fraction as a whole as my denominator gets bigger and bigger and bigger and bigger? This limit would equal 0. Minus, if I take the limit of this, well, I really don't have to worry about the limit because the limit is only concerned as t approaches infinity, but this has no t, it's a constant. And so if I do this, I believe it's 1 over negative 3, and 0 minus 1 over negative 3, or negative 1/3, is positive 1/3. What we just found is that this integral that is improper because it keeps shading forever, 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 forever to the right actually does have a set area, and that area is 1/3. So adding all of the area between the curve 1 over x to the fourth and the x-axis, and starting at 1 and going all the way forever to the right, does yield an area of exactly 1/3. It works. If this limit exists, then we say that the improper integral converges. If the limit doesn't exist, then we say that the improper integral, diverges. So just like we had convergence, divergences of sequences, here we have the convergence or divergence of an integral, an improper integral, because we're taking the limit and we're looking to see, does it actually approach a finite value? It does. That's the answer. Or does it not approach a finite value? Then that would diverge. And so we'll take a look in the next video, in the next example, how we might have a divergent improper integral, even though it looks pretty similar to number 1.